Hello everyone, welcome back to my channel Higher Mathematics. Today we have very interesting and in the same way this is a very tricky algebra question. We have 1 to the x equal to minus 2. And a lot of students might be saying, hey mister, there is no way right here we have real solution. There's no way because 1 to the x cannot be equal to minus 2. This is not possible. And here's my answer. Everything is possible in math. So right now just look at my solution to this question. So first of all, according to an exponential equation, let's apply natural log on both sides. As a result, what do we have right here? Natural log of 1 to the x we have on the left side, and on the right side we have natural log of minus 2. Right now let's write this x in front of this natural log because this is like the main log property. When we have natural log of right here we have n, right here we have p, we can easily write this p in front of this natural log. Okay, here is the main property, so we can easily write this x in front of this natural log 1. So we have x times natural log 1 equal to natural log minus 2. And right now let's divide both sides by this natural log because we need to find our x. So let's divide both sides by this natural log 1. When we divide it by natural log 1, as a result, what do we have? X equal to natural log minus 2 over natural log 1. So first of all, natural log of 1 equal to 0, so I agree with it. We can't divide by 0. And secondly, this value does not exist, so we are talking about natural log of like a negative value, so this value does not exist. So numerator does not exist, denominator natural log 1 equal to 0, so of course no real roots. But as I told before, everything is possible in math. So right now let's try to find another roots. Let's see what will happen when we remember, for example, the thing which is called Euler's identity. Okay, let's do this right now. So our identity looks like that: e to the power I times theta equal to cosine theta plus I sine theta. This is our Euler's identity. I hope you understand it. If you don't know this, you can easily look at my solution. You will understand everything about this identity. So this identity looks like that. For example, we can easily check it. So for example, theta is equal to 0. So when theta is equal to 0, we have e to the power I times 0 equal to cosine 0 plus I sine 0. Right here, this one equal to 0, this one equal to 1 because cosine 0 equal to 1, and on the left side we have e to the power 0 equal to 1. So as you can see, this identity is a correct identity. But I'm going to show you a really great substitution. So we don't need exactly this identity. We need identity with a little bit like a substitution. So first of all, just look at this substitution. Let's write it. So theta equal to 2k pi. So here's our substitution. So instead of this theta, we're gonna plug in this right here. We're gonna plug in 2k pi. As a result, what do we have? E to the power I times 2k pi. Okay, here's our identity after my substitution, equal to cosine 2k pi plus I sine 2k pi. All right, plus I sine 2k pi. So here's our identity after my substitution. And right now I'm going to show a really great trick. First of all, let's see what will happen when k is equal to 1, 2, 3, 4. So we are talking about k is integers. K is equal to 1, 2, 3, and a lot of these values. Let's see what will happen when k is equal to 1. So according to this identity, let's see what will happen when k is equal to 1. So for k is equal to 1. As a result, what do we have? E to the power I times 2 times pi, because k is equal to 1. So we have e to the power I times 2 pi equal to cosine 2 pi, okay, cosine 2 pi plus I sine 2 pi. All right, plus I sine 2 pi. And right now let's look closely. Cosine 2 pi, we can easily find it. This is like a equal to 1. Yeah, cosine 2 pi equal to 1. So this one equal to 1, and sine 2 pi equal to 0. So we are talking about 1 plus 0, which is equal to 1. So our expression on the left side equal to 1 when k is 1, when k equal to 1. Right now, let's see what will happen when k is equal to 0, or when k is equal to 2. So for k equal to 2, we are talking about e to the power I times 4 pi, okay, equal to cosine 4 pi plus I sine 4 pi. And right now let's look closely. Cosine 4 pi, this is just a period of this cosine. Okay, we are talking about 1. Yeah, this is equal to 1, and sine 4 pi equal to 0. So we're talking about 1 plus 0. This is equal to 1. And right now, really great. So right now, let's check, for example, one more example. Let's see what will happen when k, so 4k is equal to 3. Let's see what will happen. And I hope you understand it, that right here we have only e to the power I times 6 pi, so just 2, 4, 6. And on the right side, we have cosine 6 pi plus I sine 6 pi. So I hope you understand it. I just plug in, instead of this k, I just plug in this into our main, identity, okay? I just plug in this k into this identity, which is also a correct identity because I proved it in the beginning. Yeah, and equal to, right now, cosine 6 pi equal to 1 and sine 6 pi equal to 0. So as a result, we have the same one on the right side. And here is the main tricky moment. Doesn't matter what we have on the left side, on the right side, when k is 1, 2, 3, 4, we are talking about integers case. On the right side, we have all the time we have 1. Doesn't matter. E to the power I 8 pi, I 10 pi, 12 pi, 20 pi, 100 pi. We have all the time 1 on the right side. And here's a very important moment for us, because right now I'm going to write the final identity after these substitutions. We will have e to the power I times 2k pi, this is equal to 1. So this identity, this expression all the time is equal to 1. We proved it before. We can easily see this pattern. So this expression is equal to 1 when k is integer. We are talking about integers, k is z. We are talking about k equal to 1, 2, 3, and a lot of these examples, okay? So this expression equal to 1. But why we need this expression? Because in the beginning we had, so let's write it, but in the beginning we had 1 to the x equal to minus 2, and in the beginning we already know that we don't have right here real number roots. So right now we're talking about complex roots, which is also really great, and moreover we have right here our complex unit, so we can easily work with complex plane, we can easily work with complex expressions right here, because right here we know that we don't have real number solutions. So right now, instead of this 1, let's plug in this e to the power I times 2k pi. Okay, so let's do this right now. Instead of this 1, we had it in the beginning. Let's plug in this e to the power I times 2k pi. So we have e to the power I times 2k pi. We're gonna raise this to the power x, and this is equal to 1. So I hope you understand it. That's why I try to prove this identity in terms of like k is integer. And as you can see, we have this pattern, and we use this pattern in our question because this expression is equal to 1, and we're gonna plug in, instead of this 1, we're gonna plug in this complex part. Okay, right now what are we going to do next? First of all, basic school property, we need to multiply our powers. We need to multiply our powers, but I hope right here we have a little bit mistake right here. Not is equal to 1 but minus 2. Don't forget about this. We are talking about substitution to our identity. Okay, right now let's raise this to the power x. We are talking about e to the power I times 2k pi and times x, and equal to minus 2. All right, right now let's apply natural log on both sides. Okay, let's do this right now. So we are talking about natural log of e to the power I times 2k pi x equal to natural log of minus 2. Okay, I hope you understand it. We just apply natural log on both sides. Right now, this expression as a power of e, we can easily write it in front of it because of log property. I had this property before, yeah. So we have ei times 2k pi times x times natural log e equal to natural log minus 2. All right, and right now natural log e equal to 1. We can easily cancel this, and as a result we have I 2k pi x. We need to find only our x. So for this, let's divide both sides by I times 2k pi, and let's divide right here by I times 2 times k times pi. We just divide both sides by this expression. From here we can easily cancel this, and as a result we have that our x is equal to natural log of minus 2 all over I times 2k pi, I times 2 times k times pi. And first of all, let's multiply our denominator by I. So let's multiply right here by I and right here by I. In our minds, we know that I square equal to minus 1, and we have this I square right here. So we have I times I equal to minus 1. So as a result, our final sign x is equal to minus I times natural log minus 2, I times natural log of minus 2, and we divide all of this by 2k pi. 2k pi, and of course we need to know that k is not equal to 0, obviously, because we have in our denominator k is not equal to 0, and we are talking about k is integer value. And right now I'm going to show you a few thoughts about this natural log of -2, because we know in terms of real numbers there is no way that natural log -2 exists. So right now let's look at it in a perspective of complex plane. So right now let's look at this natural log of -2, and of course we're going to plug in this natural log -2 when we simplify it a little bit, when we write it in terms of like complex numbers. Let's plug in then into our formula, into our x, and we will have our final answer. So right now let's do that. All right, so a few words about this natural log of -2. So let's rewrite it, and then we're going to plug into our x. So let's do this right now. So first of all, right here we have natural log of -2. Few words about this, few notes about this expression. So first of all, we can easily write it as natural log of -1 times 2. -1 times 2. We can easily write it like that. So -1 times 2. Right now we can easily split it in terms of like multiplication, in terms of like addition, because we have natural log of multiplication. We can easily split it as a sum of two logs. So let's do this right now. As a result, what do we have? Natural log of -1. So natural log of -1 plus natural log of 2. Okay, so I hope you understand this step. We just split it in terms of like basic knowledge. Okay, and right now what are we going to do next? This natural log of -1, there is a great identity in math libraries, in higher mathematics books. This identity looks like that. We can easily change this natural log of -1 as natural log of e to the power I times pi plus 2 times pi, and times, let's use for example m, because we have a k right here, so let's use for example our m. Okay, and we have plus natural log 2. There is identity in higher mathematics books. I don't want to prove it, I just want you to know that this identity takes place. Right here we can easily change this natural log of -1 in terms of this identity. So in terms of like a natural log property, we can easily write this power in front of this natural log. So as a result, we have I times pi plus 2 pi m. Right here we have pi plus 2 pi times m, and plus natural log 2. Right now from here we can easily factor our pi, because we have our pi right here, and as a result, what do we have right here? 2m plus 1 in our parentheses, 2m plus 1 in our parentheses. We have after we have I times pi, because we factor it, and plus natural log 2. So we can easily write this natural log of -2 in terms of this thing, but m is integer. Don't forget about this. M is integer value. So right now let's plug in this. We have natural log of -2 equal to this expression. Let's plug in this expression to our x. So our x is equal to, let's rewrite it. So x equal to minus natural log of -2 over 2k pi, and we're gonna plug in this natural log, this expression instead of this natural log of -2. Let's do this right now. So we have x equal to, we have minus, right here we have I guess. Yeah, I forget about I. Right here we have I, and right here we need to write I. Don't forget about it. And as a result, we have this I times this natural log of -2. We have this expression right here. So we have, as a result, we have parentheses. We have 2m plus 1 times I pi, and plus natural log 2. Okay, and we divide all of the thing by 2k pi. Right now let's simplify it. Let's multiply our parentheses by this I. As a result, what do we have? X equal to minus, inside parentheses we have I square times pi and times 2m plus 1. Yeah, we have 2m plus 1, and plus I times natural log 2. And we divide all of this by 2k pi. 2k pi. Right here, what do we have? We have minus 1. So as a result, we have x equal to, we have minus, inside parentheses we have minus 1, so we have minus pi times 2m plus 1 plus I natural log 2, and we divide all of the thing by 2k pi. 2k pi, right here minus with this minus gives us plus, so as a result we have that our x is equal to 2m plus 1 times pi minus I natural log 2, and we divide all of the thing by 2k pi. pi. And of course, a lot of restrictions right here. So let's write our final answer to this question. So our answer, this is our answer. Let's write it once more right here in our section. So we have x equal to 2m plus 1 in our numerator times pi minus I natural log 2. This is our numerator, and we divide all of the thing by 2k pi. But don't forget about a lot of restrictions. So first of all, k is not equal to 0. K is integer value, yeah? K is integer, yeah? We are talking about k that is equal to 1, 2, 3, and 4, 5. And of course, don't forget about m. M is also integer value. Okay, so m is also integer value. So this is my answer to this question. I hope you understand it. I hope you learned something new. I hope you understand my note about it. But this is not a general solution in terms of, like, you know, we don't know what will happen when k is negative value, when k is minus 1.5, when k is minus 20, when k is minus 50.25, yeah, something like that. So we know everything about this answer when k is integer, when m is integer. So this expression takes place. But as I told before, this Euler's identity, we don't know what will happen when k is 2.5, for example. We know everything about when k is integer. So when k is integer and m is integer, this answer is great for us. But we don't know what will happen when k is like infinity, minus 2, minus 3, minus 5.5. We don't know about it when we have a decimal values, when we have fractions, when we have radicals. We don't know what will happen there. So this is like a special case when k is integer and m is integer. Also, you can write your thoughts. It would be really interesting to exchange information. Write your notes about this question. What do you think about it? What identity you prefer about this question? What do you think about it? It would be really interesting to read about it. It would be really interesting to exchange information, and I hope you understand it. I hope you learned something new. Also, write your notes about this challenge. What do you think about it? Let's exchange information, because a lot of teachers maybe watch my videos, and it's really great to exchange with your notes, with your thoughts about this question. This is not like a general school question, but it also takes place. For example, if you want to think a little bit about complex part, to think a little bit about this part when 1 to the x equal to minus 2, what will happen there. So this is only my notes about it. This is my solution. Also write your solution down to the comment section. It will be really interesting to read about it. So thank you everyone for your time. Wish you all the best in your life. See you in the next videos, and have a great day.